In 1943, the Pajarito Plateau in northern New Mexico was transformed for a top-secret, wartime scientific project to harness the power of the atom, to discover and deliver an atomic bomb, to determine the outcome of World War II. It was a scientific enterprise unlike anything the world had seen. Top scientists from around the world led the effort at present-day Los Alamos. Previously, they only knew each other by reputation. They came together at a laboratory that didn't exist and delivered not just a scientific breakthrough, but a product that worked. The Trinity test, the world's first nuclear explosion. This was groundbreaking science and engineering. It was not a foregone conclusion that the gadget would work. On July 16, 1945, at 5:29 in the morning, the Trinity test was unambiguously a success. The implosion worked, and that same underlying science led to the end of World War II within less than a month. It's also the case that science was changed forever. 18 Los Alamos scientists had either already won the Nobel Prize or went on to win it. That's certainly a measure of the fact that the best and the brightest came to Los Alamos to solve a very hard problem, but arguably even more important, the set of folks who went on to win the Nobel Prize after Los Alamos learned how to do science by the experience of Trinity, and that's a big part of the legacy of the Science of Trinity.
I view the Trinity test and the Manhattan Project as the existence proof for the fact that science has an enormous impact on national security. And that was not appreciated before the Manhattan Project. It brought together the organization and it relied on the fundamental science and the scientists in order to be able to make it work.
No one field of science would be able to do something as monumental as Trinity because there were so many fields of science that were required. It really does represent the capstone of decades of innovation and discoveries in many fields coming together for an important purpose during the deadliest war in human history.
Normally, when we think about science, we say that we can't schedule discovery. That was different in the Manhattan Project. There was clearly a deadline and an urgency that went with it.
And a big motivator for a lot of the scientists was the fear that Nazi Germany would create this weapon and have a nuclear monopoly before we would. And this was a pretty legitimate fear. Fission had first been discovered in Nazi Germany, and a lot of the scientists who came to Los Alamos were from Axis powers, and they were very aware of the scientific capability of Nazi Germany.
The Manhattan Project welcomed the best in the world to come and work here at Los Alamos. In many cases, they were people that fled Hitler's Germany. So you had all of these incredibly bright scientists, and we welcomed them with open arms into the most sensitive project of the American government during the Second World War.
A remarkable group of scientists, some of the greatest minds in the world. And in an amazingly short time, less than 2 years, they were able to create concepts for weapons that proved workable. But they had also created a whole range of new technologies in experimentation, nuclear science, material science, chemistry, metallurgy, computing, simulation, theoretical physics.
And the fact that Manhattan Project scientists could translate discoveries to product against an urgent deadline was a key feature of Trinity science.
One of the great traits of the researchers at Los Alamos during the Manhattan Project was their adaptability.
The scientists and engineers had decided that we would take the two paths to the bomb, plutonium path and the uranium path. And the initial design was the simplest design, and that's a gun type assembly.
Part of the way through the program, it became apparent that plutonium was not going to work for a gun-assembled device. And at that time, the entire workforce rapidly reoriented to focus on developing an implosion device using plutonium.
The Trinity experiment was conceived because a proof of principle was needed, a confirmatory experiment was needed to prove out this completely new pioneering implosion concept. But to understand that, we have to jump back a year earlier when Segre made a key nuclear data discovery related to plutonium spontaneous fission that led to the lab abandoning the gun bomb idea for plutonium.
They had the type of talents that made it possible in this incredibly short period of time to completely switch over the design for the plutonium bomb to an implosion.
That implosion concept involved lenses of high explosives compressing a solid plutonium gadget. But Oppenheimer and Groves realized that there was sufficiently number of new features in this concept that it had to be experimentally tested before it could be used in combat.
And so basically in 10 months, this goes from being made a major effort at the laboratory to being successfully field tested. And then just a few weeks later, in August of 1945, implosion weapons, Fat Man, entered combat for the very first time, again successfully. It really shows how versatile the staff was under great pressure during World War II.
It's often the case in science that we talk about standing on the shoulders of giants. One of the things that's most inspiring about the science of the Manhattan Project is that there were no giants on which to stand. They defined the field. Plutonium barely existed in its atomic form when the war started. The fields of actinide chemistry, of plutonium metallurgy, and nuclear physics as it applies to various kinds of nuclear fission were invented and created for the very first time at the Manhattan Project.
In 1941, there was less than a microgram of plutonium that had been discovered, and that generated three main chemistry challenges for the Manhattan Project. The first challenge was to find a method for the production of plutonium on a large scale. The second was to devise a method for its chemical separation and purification. And the third was the scale up of the chemical separation from micrograms to tens of kilograms. That's a factor of 10 billion. Fortunately, Enrico Fermi solved the first problem by demonstrating the first nuclear chain reaction in uranium in December 2nd, 1942, meaning that you could prepare plutonium in a nuclear reactor. The problem of separating and purifying plutonium, however, came down to understanding the chemical properties of plutonium well enough that you could separate plutonium from the enormous quantities of fission products and uranium. Getting it separated and purified was absolutely essential for safe handling. At the end of the day, 1 to 1.5 tons of fuel would result in 300 to 450 grams of plutonium per day. Moving from the discovery of a few atoms of plutonium to a scale-up of tens of kilograms in a huge industrial process was one of the great technological achievements of the 20th century and one of the great legacies of Trinity.
A key challenge of the actinide science of the Manhattan Project was understanding plutonium metallurgy. The metallurgists had to figure out what its properties were and how to machine it in a form that worked for Trinity.
The most complex element in the periodic table. And it's the most complex element not because of its nuclear structure, but because of its electronic structure. And its electronic structure then governs essentially all of the metallurgical and the engineering properties of the material.
It turns out that plutonium in its pure form behaves like cast iron. So one of the challenges Manhattan Project scientists had to take on was, could they alloy plutonium to make it a more useful form?
And the guy who was leading that charge was as much of a hero for the metallurgist as many of the physicists like Hans Bethe or Enrico Fermi or Oppenheimer would be for the physicists, and that was Cyril Stanley Smith. And what the metallurgists were able to do, led by Cyril Stanley Smith, one of the foremost metallurgists of that time, they were able to essentially tame this exotic element.
They developed alloying strategies for plutonium to stabilize a structure that was ideal at room temperature.
If you add a little bit of aluminum, it makes the plutonium behave significantly better from an engineering standpoint. But as it turns out, the physicists didn't like the aluminum addition. It would actually give what we call an alpha N reaction and make neutrons. And once you make neutrons in something you're trying to implode, then you can get a fizzle. And so at that point, then they moved back and said, okay, let's go down the periodic table, get the same sort of chemical alloying effect, but get a heavier alloying element, and that was gallium.
And in fact, today we still use plutonium-gallium alloys. Those are our state-of-the-art for plutonium metallurgy.
As we look at the challenges we still have with plutonium, in a world without nuclear testing, we need to understand things better. We need to be able to use all of the latest tools, be they new experimental capabilities, be they advanced computational capabilities. And that's where the next generation comes in. So I would say we left enough for the next generation to actually be able to understand plutonium better so this laboratory can continue to do its job of stockpile stewardship.
The Manhattan Project coincided with the birth of nuclear science. So much was not known at the time. Interestingly, at the beginning of the project, there were some very lucky guesses they had. They were tremendously clever and intuitive people. Oppenheimer and Bethe and colleagues actually had a pretty good guess at the first critical mass of plutonium based on their understanding at the time. But during the project, they realized that they had to determine the fundamental fission cross-sections, fission spectra, the multiplicity of neutron emission accurately to be able to calculate the efficiency of the weapon and to be able to design the Trinity test. Bethe was very articulate about the need to understand those fundamental constants. And in the process, they had some great surprises, some great discoveries, and some tremendous disappointments. The main disappointments were that their first guess at the plutonium fission cross-section turned out to be a lot lower than what they expected. However, luckily, balancing that, the multiplicity of neutrons turned out to be far higher for plutonium than uranium, and they hadn't expected that. Of course, there was also the famous story of Segre's discovery of the importance of plutonium-240 fission, but that had the golden lining of the fact that the implosion concept was developed. By the end of the project, Los Alamos was recognized as the leader in the community for nuclear science. Vast breakthroughs occurred in computational simulation, in fundamental nuclear theory, in accelerator development, and these subsequently led to some of the important breakthroughs in science in the 20th century.
Trinity was the first product of the union between big science and large-scale scientific computation. It introduced a whole generation of theorists and experimentalists to the power of numerical solutions to otherwise intractable nonlinear problems. The first computers at Los Alamos were human. They were mostly women drawn from the families of the scientific staff. Josephine Elliott, Michi Teller, Kay Manley, Mary Frankel were among the first computers to work at Los Alamos. By the summer of '43, professional computers from the Women's Army Corps augmented the computing staff to about 20 computing personnel. Later that year, Hans Bethe discovered that the hand computing effort was being overwhelmed by the volume of neutron diffusion calculations, and under recommendation he ordered a collection of IBM punched card accounting machines that could augment the hand effort. By the time the machines arrived in 1944, the lab's main research effort had shifted to the implosion weapon. Oppenheimer brought John von Neumann, the renowned mathematician, on board. Von Neumann confirmed that implosion was going to be an efficient design choice, but it would require a massive computational effort to make it work. The human computers and the IBM punch card equipment were called upon to conduct simulations to determine which design would be the most viable. The final design of the Trinity device was selected by the lab's leadership in large part based on the simulations demonstrating that it was the design with the greatest chance of succeeding. The success of Trinity validated the computational effort, and it demonstrated to a generation of scientists the power of numerical simulations for solving problems that otherwise couldn't be approached. The work on Trinity also spurred a lot of key figures to pursue new technologies and methodologies. One of the most important of these introductions was John von Neumann introducing Los Alamos to the ENIAC project, which resulted in the first large-scale computation ever done, which was a feasibility assessment for thermonuclear weapons. in the SEC today, the aptly named Trinity supercomputer is the culmination of a long process of Los Alamos being deeply involved with the development of digital computing, extending all the way back to the Manhattan Project.
So one of the most important tools that came out of Los Alamos was a demonstration of how important computing is in these technological enterprises.
For more than 70 years, Los Alamos has invested in and helped discover the state-of-the-art of high-performance computing and applied those computational techniques when partnered with advanced simulation and theoretical models to predict the performance of our weapon systems, either when we validate them in testing or in the last 25 years since we've not done any nuclear test and yet retained our predictive confidence in the nuclear stockpile. An important element of the success of science during the Manhattan Project and in Trinity was that the goal was not just a scientific result, but actually a product that worked. Advanced imaging was critical to understand how the weapon was performing and if it would work.
How do you look inside this device and see how smooth that implosion is so that you can predict what the performance is going to be? The Trinity Project developed 3 kinds of radiography. RALA stood for radiolanthanum. They put a radioactive source in the center, which generated gamma rays that you could measure on the outside to get an idea of what was going on in that imploding shell. The X-ray method was essentially taking commercial off-the-shelf X-ray machines, turned out to be too complicated. However, the X-ray work was very good for small scale, so the X-ray method kind of changed course in providing critical information to the project. The most successful radiography method was the Betatron method. The best source available was the newly developed Betatron. The best detector was the cloud chamber. So they coupled these 2 technologies together, getting a shadowgram of the inside of the imploding device. As the stockpile evolved, we developed Fermex. This high-energy electron accelerator produced X-rays that could penetrate the large-scale implosions. It was a workhorse for the developing stockpile at the time. In 2008, born out of stockpiled stewardship where we knew we couldn't test anymore, we needed even better and better data of what was going on inside that implosion. That was the advent of the dual-axis radiographic hydrotest facility, known as DART. DART provides exquisite pictures from different views and in different times. The clarity of the pictures at DART, the drool factor, is impressive.
The Science of Trinity clearly changed the arc of the fields of actinide science, of advanced imaging, and of simulation and computing. But perhaps more importantly, Trinity science represents a change in how we do science.
One of the things that Trinity really taught us as a laboratory was how to take on problems that are unusually large and complex and multidisciplinary.
The Manhattan Project is a term that has entered our vernacular to describe a program that requires expertise in a wide variety of areas and a large number of experts to execute.
The Manhattan Project and the Trinity test, which was the culmination of the scientific part, changed the world, and it changed the world dramatically.
Although Trinity demonstrated the possibility of atomic weapons, and in fact 2 were used shortly thereafter, for the intervening 75 years, nobody has used nuclear weapons because showing that they were possible and showing their destructive power
brought a sense of restraint and stability to the enormous rate of killing that we saw in the first half of the 20th century.
The Manhattan Project, when you look at it as a whole, and of course its scientific culmination was Trinity, represents a new era in human history. And that's something that cannot be said of very many individual events, or many times in history. It was the advent of a new age, and an age that would be full of incredible promise as well as unprecedented perils.
The legacy of the Manhattan Project and Trinity is certainly the United States' nuclear deterrent and our national security enterprise. And in fact, the entire family of Department of Energy national laboratories grew out of the success of the Manhattan Project, leading to the scientific infrastructure that we in the United States have today.
So to me, as I look back, it was this remarkable accomplishment by the scientists, engineers, the military people, administrative people here at Los Alamos and in the complex that made it happen. And to do it in a time scale that was remarkable of some 27 months, brought the scientists together, made a direct contribution to our national security and to the future of the world.